Hello everyone, let us start today's session. This is live session number 3 and in the today's session we are going to discuss the important points related to the design of different types of substation and specifically we will in today's session we are going to solve problems based on the power loss and voltage drop across the feeder in different types of in different specific type of distribution substation. So let us begin today's session. So first point is that this is very important, we should know about the K constant. K is a constant that can be defined as a percentage voltage drop per kilovolt per ampere per kilometer. So here if, I have written down this expression. So this is the K expression.
Sir, only your peak is showing, not screen of the
Okay.
content.
Oh, thank you. I have not shared actually. Now I think it is visible.
Yes, sir. Yes, sir.
Yeah, if you have written down this expression in this way, this has been derived in the class. So here the k is equal to r cos theta plus x sin theta into 1 by third of 1000 divided by Vr into Vs. So 1000 comes here due to this kVA and 1 by third is divided for the per phase value. In this expression, you will get we will having resistance. We should know about the resistance of line per unit length and X is reactance per unit length. Then we are given with cos theta, that is power factor of the load, and we should also have data of receiving in per phase voltage. Receiving in per phase voltage, and then V base. V base is the base phase voltage. So if you use this expression, that will give you K in the terms of voltage drop per unit by kVA mile, and if you multiply it with 100, that will give you percentage voltage drop per kilovolt ampere kilometer or mile. So based on here I have used mile, so you can write here mile also, no problem. So depending upon the problem, you just change the expression. So on this expression we are going to solve the first problem. So the first problem is that assume that a three-phase 4.16 kV a star grounded feeder main has copper conductors with equivalent spacing of 37 inch between phase conductors and operating at a lagging load power factor of 0.9. The length of the feeder is 2 miles. The conductor specification is given as resistance is equal to 1.503 ohm per mile, and leakage reactance is called 0.7456 ohm per mile. Assume the base voltage line to neutral as 2400 volt. Determine the per unit voltage drop per kVA mile of the feeder. And the options are this one. So as I told you, just use the previous expression. And the previous expression we have written down the expression in per unit voltage drop per kVA mile. So the same expression we are going to use. Per unit voltage drop per kVA mile is, so it is denoted by K, and we have the expression as R cos theta plus X sin theta into 1 by third of 1000 divided by VR V base. So here what are the values we have in the known. R is given as 1.503 ohm per mile, and reactance is given as 0.7456 ohm per mile. Cos theta is also given. Cos theta, it is lagging load power factor, that is given by 0 0.9. Therefore sin theta will become 1 minus 0 0.9 whole square, so it will become 0.4359. Okay, so we are here. So sin theta we got 0.4359, and we have to know the receiving in per phase voltage. So we can, so we can write this is three phase voltage is given. So we have to convert into phase value. So 4160 divided by root 3, it will give you 2400 volt, and base phase voltage is also given as 2400 volt. 2400 volt. Now just we have to substitute all these values. K equal to 1.503, cos theta is 0.9, and x into sin theta 0.7456, sin theta is 0.436, multiplied with 1000 divided by 3 divided by 2400 whole square. So on simplification it will coming as 559.233 divided by 2400 whole square. So it will coming as 9.7089 into 10 to the power minus 5. So it is coming as 0.00097. So approximately 0.0001. So this value of K we got in terms of per unit voltage drop per unit per kVA mile. So if someone asked you here that percentage voltage drop, then what you have to do? Can anyone tell? Rahul, Dharmender, Sangeeta. So this value we got in per unit. If anyone asked in terms of percentage voltage drop, then what should be the answer? Because this type of question is asked in assignment 4, so you should know the thing. So here be the correct answer. Now if they told you to find the answer in the percentage form, then in percentage form it will be written like you should just multiply it with 100. So it is coming as 0.001. So this will be percentage voltage drop per kVA mile. You should just multiply it with 100. Sorry, if multiply 100, then it will become 0.01. But here in this problem, it is asked for per unit voltage drop. So B is the correct answer. Now let us move to the next part. So the so we will solve problem based on this power loss and voltage drop. So the important expression you should know about the power loss and voltage drop for radial feeder with uniformly distributed load. So we are dealing with uniformly distributed load. Radial feeder with uniformly distributed load. So as we can see here that this is primary feeder and these are laterals, and each load is represented by the in the node form. These are the nodes. So we can see that the loads are distributed among in the radial feeder in uniform way. So if you go for computing voltage drop and power loss, then it will come as voltage drop will be half is ZL. So we can see that the voltage drop will be similar to a lump load connected at the midpoint of the feeder, that X is equal to L divided by 2, and total power loss if you compute, then it will come as 1 by third of Is square RL. So this will be if you compared with the lump load or concentrated load, then you can see that you can assume that a lump load is connected at one third of the length of the feeder. That means X is equal to L by 3. So this uh, power loss is given in the form of per phase power loss. If they are asking about three phase power loss, then you should multiply this by 3. Then you will get the total power loss. Any doubt till here, Dharmender? Another one, Sangeeta.
No, sir. Thank you, sir. One thing I would like to ask: third week discussion is not uploaded on NPTEL Operation Planning of Power Distribution System. Only 2 weeks links are given.
Actually, in the first session, in the first live session, we discussed the assignment 1 and 2. Okay, so
Yes,
that's
sir.
why we are we are ahead of the assignment. Like in week 3, we are going to discuss the assignment 4. So, like we have two live sessions.
Yes, sir. So in second live session, you have discussed about third assignment.
Yeah,
I hope.
third assignment. Yes. Have you
Okay,
gone
sir.
through
Thank you.
this assignment 4, Dharminder? Have you
Yes,
gone
sir.
gone through this assignment 4?
Yes, yes, sir. Yes, sir.
Okay. So we are so one thing I want to just make clear, in week 1 live session we have discussed assignment 1 and 2 both combined, and in week 2 we have discussed the assignment 3, and in week 4 in week 3 we are going to just show on it will continue. Each assignment will be covered in subsequent week. So this is very important that if they are asking about the informed distributed load, then you can assume that if you are if you are they are telling about the voltage drop, then just assume that one load, sorry, one load that is concentrated at the X is equal to L by 2, and if they are they are telling about the total power loss, then you can assume that a lump load is connected at one third length of the feeder. So these two expressions are very very important for the radial feeder with uniformly distributed load. So now we will solve the problems based on these expressions. So let us see this problem number 2. So a distribution feeder with uniformly distributed load of rectangular service area is carrying 100 ampere of current at the sending end side, substation side. The length of feeder is 5 km and the resistance is of 2 ohm per kilometer. Determine the three phase total power loss of the feeder. And the options are given here. So just you solving this problem, and whoever is getting the answer, type your answer in the chat box. So in this problem, what are things we have given? We are given with IS. IS is sending end current, Sending end current is given by 100 ampere, and L is length of feeder. Length of feeder, that is given by 5 kilometer, and resistance of line is given. Line resistance is given by 2 ohm per kilometer. In this case, we have to compute the total power loss of the feeder. So power loss per phase will be half 1/3 of Is square RL. So this we know from this expression. Per phase power loss is 1 divided by third of Is square RL. So 1/3 of Is is 100 square. R is given as 2 ohm per kilometer and L is given as 5. So you will get this value is 33.33 kilowatt. Therefore, three phase power loss equal to 3 into 33.33 kilowatt. So this will come as 100 kilowatt. So correct answer is A. So just be careful. This is per phase power loss expression, not the total three phase power loss expression. So in the computation of three phase power loss, what we assume the effective length of feeder if we concentrate the load at one point? Can anyone tell? Anyone can give answer. My question is that yes, I yes, anyone wants to speak?
Sir, repeat the question.
Yeah, I am asking the question that in the radial distribution feeder with uniformly distribution load, just like this case, the and the picture shown over here, if the if you assume the concentrated load irrespective of the uniformly distributed load, then what should be the effective length of the feeder? Did you get? Did you get my question? I think you did not get my question. So let us we will discuss later. Let us solve one or two more problem. So let us coming to this problem. Question number 3. An 11 kV three-phase distribution feeder with uniformly distributed load of rectangular service area is carrying 100 ampere of current at the sending end side, that means substation side. The length of the feeder is 5 km and the impedance is 2 ohm per kilometer. Determine the percentage voltage drop of the feeder with respect to the phase voltage. So the data are same in this just as the previous problem, but in this problem they are asking about the percentage voltage drop with respect to the phase voltage. So we know that expression total series total series voltage drop along the full length is, so voltage drop is given by half of Is ZL. So this expression we have seen in the previous slides. This voltage drop is equal to half of Is ZL. So just apply this expression. So Is is given as 100 ampere, Z is given as 2 ohm per kilometer, and length of the feeder is given as 5 kilometer. Therefore, voltage drop will be half of 100 ampere, and Z is 2 ohm per kilometer, and L is 5 kilometer. So you will get 500 volt, that is equal to 0.5 kV. So they are asking about the percentage voltage drop of the feeder with respect to the phase voltage, right? So we have to compute the percentage with respect to phase voltage. So we can write percentage voltage drop with respect to phase voltage. It will be 0.5 kV. So phase voltage we have to find. So phase voltage we can find. Phase voltage will be line voltage divided by root 3. So 11 divided by root 3 kV. So it is coming. So whatever the value we will put in the final expression. So 11 root 3 will go top and multiplied with 100. So you will get in percentage form. So you will, this will coming as 7.87%. So see the correct answer. Anyone got the answer? Yeah, Rahul Patil is getting the correct answer. For Sangeeta, for uniform load, effective length is half actual length, half of length lumped. Yeah, for uniform load density, yes, correct. For uniform load density, if we are computing the percentage voltage drop, then you have to, then the effective length will be half of the total length of feeder. And if you are finding the power loss, then the effective length will be one third of the length of the feeder. Just we have seen in this slide that question I was asking previously. So for voltage drop, the effective length will be half of the length of feeder, and for power loss, the effective length will be the one third of the length of the feeder. Now let us come to the next problem. So the generalized form of the percentage voltage drop of the main feeder you can write in this form. Percentage voltage drop n representing the number of feeders, and K is the percentage voltage drop per kVA kilometer of the feeder, and L is the effective length of feeder, and Sn is the kVA load served by one of the feeders. So I can write here. So in this expression, K is percentage voltage drop per kVA kilometer of the feeder. and L is the effective length of feeder. We have previously computed voltage drop in terms of if we are given with the line impedance and the current flowing through the feeders. But if you are given with this percentage voltage drop K constant and if and this load load value of the feeder, then you can use this expression. Effective length of feeder and SN is kVA load served by one of n feeders. So this expression we are going to use in this problem. So problem, let us see the problem. So this is problem number 4. Here the problem says that assume that an 8-mile long feeder is supplying a 2500 kVA load of uniform load density and rectangular service area. If the K constant of the feeder is given as 0.0001% voltage drop per kVA mile, determine the percentage voltage drop in the sorry, I think there is some problem. Determine the percentage voltage drop in the main feeder, you can say. Here little bit typo error in the problem. So just ignore this and solve the problem. You have to find the percentage voltage drop of the feeder. So for informed load density, what is the effective length of the feeder? Can anyone tell? For if you are finding the percentage voltage drop, many are typing their answer in chat box. I am getting some of answers also. Voltage drop option A, question 4. Yeah, you are correct, Sangeeta. Very good. So as she said, so effective length will be L divided by 2 if we are informed load density with rectangular service area. So just put all these values. Percentage voltage drop equal to K into LESN. K into L divided by 2 and S is 2500 kVA of informed load density. K is given as 0.001 percentage voltage drop per kVA mile. Write the unit also so that if unit doesn't match, then your answer might get wrong. 8 mile divided by 2 and S is given as 2500 kVA. So you will get 1.0%. So A is the correct answer. If you are having any types of doubt, then you can ask. Otherwise you will not understand what I am solving. Any type of any that is very important. I think this is little bit terminology are there. So just get familiar with terminology and nothing is more complicated here. Here some terms are there like a constant, effective length, and they are we are representing by different symbol. So just get familiar with this. You will not get trouble while solving the problem. So now let us see the next problem. So before solving the problem, we will see triangular service area. In the if there is radial feeder with uniformly distributed load, and that will make triangular service area. So some where it is written like that, uniformly distributed load with triangular service area, and somewhere they may write like that, non-uniformly distributed load with increasing load density. So both having the same meaning. Means they, if there is triangular service area and the loads are distributed, then the image will come in your mind like this. And some, if someone is saying that there is non-uniform distributed load but with a linear increasing load density, so that will also have the same meaning. Means this image will come into your mind. So in this case, if you compute the voltage drop, then it will come like this: 2 2 2 divided by third ISZL. Therefore, to determine the voltage drop, the total load current is assumed to be concentrated at 2 by third of L. And if you are computing the power loss, then it is coming as 8 divided by 15 IS square RL. So in this case, you can assume that total load current is assumed to be concentrated at X is equal to 8L divided by 15. So this is the effective length that you have to assume that uh, lumped load is concentrated at this length of the feeder, 2 by third of the total length of feeder. So did you understand? Anyone have a doubt in this slide? How we are computing this effective length or anything? So uh, these relations we are comparing with concentrated load like in this way. Suppose this is a radial feeder and we are having assume that one load is connected at the one, only one concentrator load is connected at the end of the line. So here one load is connected at the end of line. So in that case, what will the percentage voltage, what will the voltage drop? Voltage drop is just simple, whatever the current flowing through it. So IS, and Z is unit length of uh, per unit length of per unit length impedance, and L is the length of line. So if you compare this with this, then you can say that effective length will be 2L divided by third. So from here we are comparing that if we are having concentrated load, then what will be the things, and if we are having this type of informally distributed load with triangular service area, then what will the voltage drop. So this is the summary for the radial feeder for uniformly distributed load with triangular service area. For this type of figure, you have to just keep in mind this voltage drop and power loss. In voltage drop, the the total load current is assumed to be concentrated at 2 by third of length of feeder, and for power loss, total load current is assumed to be concentrated at 8 divided by 15 of length of the feeder. And in this, here I have shown with the voltage drop, you can show with the power loss also. So if you want to write the power loss, in the simple case, it will come as IS square into RL, because all the load we have concentrated at the end of the line. We have assumed that only one load is there and that is connected at the end of the line. So let us see the next problem, and I hope everyone can answer this problem. So this is problem number 5. So in this problem, if the original length of the feeder is L unit length, then what will be the effective length of the feeder when the load has uniform load density with triangular service area? Yes, what should be answer? Can
Sir,
you?
D option D.
Yeah, correct. So D is the correct answer. The effective length of the feeder will be 2L divided by third. So we have seen in the previous slide. For voltage drop, we can see that we are assuming that concentrated load is connected at the 2 by third of length of feeder. So D is the correct answer. And from here you can see from this figure, whatever the loads are informally distributed having triangular surface area, we are for the effective length for while computing the voltage drop, we are assuming that all the loads concentrated at the 2 by third of the length of feeder. So it is being represented by this 2 by third of L4. So let us see the next part. So now we are moving to the more complex type of distribution substation having different type of service area. So let us see that for the case where we are having n primary feeders and the n value should be greater than equal to 3. So let us see this case. So this is generalized case having substation service area with n primary feeders, and here we have assumed n greater than equal to 3. So in that case, if anyone asked you to area served by one of n feeders is, for that the expression is an is equal to ln square tan theta. So this is the expression. So here we can write ln is the linear dimension of the primary feeder service area. Linear dimension of the primary feeder service area. In simple way, you can say that this is the length of the primary feeder. And tan theta, it is in unitless quantity, so we will get ln square, that is mile square is the eh, unit of area, and theta we can write theta is equal to 360 divided by 2n. And n is the number of primary feeders. N is the number of primary feeders. N is the number of primary feeders. So if you in another way you can say that why it is not effective for n is less than is equal to 3. If you substitute n is equal to 1, then tan it will come as tan 80 degree, tan 180 degree. So tan 180 degree is 0. So it is not effective for n less than equal to n less than equal to 3. And if you put n is equal to 2, then it comes as tan 90. And we know that tan 90 is infinity. It's like that. So this is the area served by one of n feeders. And now the next thing is that KVL load served by one of n feeders. it will be computed by this expression Sn is equal to d into An. And this is kVA load served by n feeders, so this unit is in kVA, and d is load density, and load density unit is given by kVA per mile square or kVA per kilometer square, and area unit is given by mile square or kilometer square. So this is kVA load served by one of n feeders. Now the percentage voltage drop of the main feeder will be, we have seen this expression, K into LE Sn, and the effective length for the feeder having uniformly low density with triangular service area, we know that effective length is 2 by third of ln. So total or lump sum load is connected at a point on the main feeder at a distance of 2 by third of ln from the feed point. So this is the also important, 2 by third of ln. Now we put all this expression and we will get the generalized expression of percentage voltage drop. So you will get this expression. How we are getting this expression? Just I will write percentage voltage drop, we got K into LESN, and we know that for uniformly distributed load with triangular service area, effective length is 2 by third of ln into Sn. So, so percentage voltage drop is 2 by third ln, and Sn we can write d into An, and again K into 2 by third of ln, and An we can write ln square tan theta, and tan theta we know that theta equal to 360 divided by 2n. So you will get this final expression, this one. Now just for assuming the case, if you have a square service area where four primary feeders are there and have each primary feeder has a triangular service area, in that case what will be the percentage voltage drop across the each feeder? So you have to just use this value, like theta is equal to 360 divided by 2n, we know that. So if you put n is equal to 4, you will get theta is equal to 45 degree, tan theta is equal to 1, and then percentage voltage drop, you will get k into 2 by third of d into L for q, and for n is equal to 6, you will get theta 30 degree, and tan theta we know that it is 1 divided root 3, and put in this expression you will get percentage voltage drop in this way. I think in the assignment 4 they are asking about the octagonal substation service area, octagonal. So in that case number of primary feeders will be 8. So what will be the theta value? Can anyone tell? For if there are 8 primary feeders, I am not getting response today that much like previous two. Sangeeta, do you have any doubt? Yeah. So she has doubt for lump load, L is equal to L, whereas in firm load 2 by third length. Can you kindly confirm? It is also solved in one of the examples by Saurabh sir in week 4 For third lecture example, someone. I'm not getting your problem. Can you elaborate, Sangeeta? You mean to say that Sanjeev Ganguly, sir? Professor name is Sanjeev Ganguly. I think you mistakenly wrote Saurabh. Okay. For lump sum load L is equal to 12, whereas in form load 2 by third length. Yeah, 2 by third means I think you just got mistaken by this. Someone mic is turned on. Could you please turn it off? So if you're finding the percentage voltage drop in these two cases, in this case it is uniformly distributed load and in this non-uniformly distributed load with triangular service area. So in this case, effective length will be L divided by 2, and in this case effective length will be 2L divided by third. That is the simple case. You can see the derivation of this also. Did you get my point, Sangeeta? In slide number 10, sir, it is written no inform load as 2 by third. Yeah, that I am reading. But as per sir lecture, he told effective length equal to actual length. Yes. Yeah, for non-informed load means this case, having triangular surface area, then effective length will be 2 by third of L. And this informed load, that means effective length will be L divided 2. You have to assume the half the length of feeder. It is simple. It is not that much complicated. Did you get? Yeah, good. So here I think it is also mentioned 2 by third of the length of feeder. We are concentrating at it is the effective length of feeder. Now, sorry for this trouble. We could join in the another session, and because 1 hour is, I think it is going to over. So I have shared one link. So all of you please join by this link, and we will continue after that. So all of you please join by this session. Now now I am ending this session. Okay, all right. Now I think everyone joined. S- Now I think everyone joined, so we can continue in this meeting. So we are here. So I'm asking that if we are having eight number of primary feeders, then what will theta value? Could you please type it in chat box, or if you want to speak, then you can tell also. Sujata, Jaswant, Rahul, Dharmender, Sangeeta. Only four attendees are here. More you will get interacted, more you will learn. So just a little bit, you should be interactive.
Actually, sir, I am just preparing right now third assignment and fourth assignment I have seen, but I have not go through the all the lectures of regarding the fourth week.
Okay,
That's why I have some difficulty regarding that today.
okay, no problem. So 10, it will come as 0.4142. Accordingly, you can find percentage voltage drop for this case if we are having octagonal substation service area. Now let us come to the next problem. So here, this substation area, I just want to mention for this, if we are having four number of primary feeders, then it denotes the a square substation service area. And if we are having six number of primary feeders, then hexagonal substation service area. And if we are having eight number, then it represents octagonal substation service area. So let us see the next problem. This is question number 6. Now I have to little bit move faster. So in this problem, a distribution substation is having four identical primary feeders with a square service area. The substation located at the center of service area. The service area of each feeder is of triangular with uniform load density of 1000 kVA per kilometer square. The voltage of each feeder is 11 kV three phase. Each feeder is of thermally limited to 100 ampere. Assume constant K is equal to 0.0025% voltage drop per kVA kilometer. Determine the length of each feeder. So I think all the data are given and we have to just fill in the percentage voltage drop. Given things are K equal to 0.0025 percentage voltage drop per kVA kilometer, and D is given as 1000 kVA per kilometer square. And for triangular service area, we know that effective length is 2 by third of ln. So it will be 2 by third of L4. 4 representing the number of primary feeders. Therefore, we can write the KVA load served by one of n feeders is S4. S4 is D into A4. A4 is L4 square tan theta. And for a square service area, we know that it theta is equal to 45 degree. So D L4 square tan 45 degree is D into L4 square. So we have seen in the previous case that percentage for fourth, in this case for uh, for fourth number of primary feeders, this percentage voltage drop is 2 by third of D into L4Q. So we will use this formula only. Percentage voltage drop will be K into LE. I am just driving it also. SN. So LE is 2 by third of L4. SN is D into L4 square. So percentage voltage drop will be K into 2 by third of L4Q into D. So just put all this value. K is 0.00. Sorry guys. So we are here. Yeah, sorry. 0.0025 into 2 by third of L4Q. L4 is 1.38. So L is also not given here. So first we have to find the L value. Sorry, I have one mistake I did. Sorry for in this problem we have to find the length of feeder. I mistakenly find all these things. So how will we find the length of each feeder? We have to find the length of each feeder from the value that is thermally limited feeder, that is maximum load current of one feeder. From there we can find the length of each feeder. So for length of each feeder we need the value of load density. Here load density is given as 1000 kVA per kilometer square. So that means 1 VA divided by meter square. So VLL will be line to line voltage given as 11 kV and number of primary feeders is given by 4. And this feeder is limited by, this is thermally limited feeder. So that means maximum load current of one feeder is maximum load current of one feeder is given as 100 ampere. So it can be written as I4 equal to 100 ampere, and we can write I4 as S4 divided by root 3 into VLL equal to 100 ampere. Now S4 we can write in the form of load density dA4 root 3 times of VLL 100 ampere, and for the square service area we know that A4 we can write L4 square tan theta, and tan theta is 45, tan 45 degree will be 1, so it will be coming as A4 equal to L4 square. So this will be D into L4 square divided by root 3 times of VLL equal to 100 ampere. So D is given as 1 volt ampere per meter square. It is multiplied with L4 square divided by root 3 times of VLL 100, and VLL is given as 11 kV, 11 into 10 to the power 3. So L4 you will get 100 into root 3 into 11 into 1000. So if you compute this, L4 will come as 1380.13 meter. So that is approximately coming as 1.38 kilometer. So B is the correct answer. Any doubt in this problem?
Sir, please can you repeat about this load density that you convert? I thought it's supposed to be 1000 VA per square meter.
Yeah, sure. So it is, so I just write kVA into VA. So it will be 1000 VA, and each kilometer will be written to 1000 meter and 1000 meter. So it will be 1 VA per meter square, right?
Oh, okay.
Mhm. So let us move to the next problem, and most of the part we have solved. So in this problem, determine the percentage voltage drop of the feeder for the problem given in question number 6, the previous problem. The same thing, we will use this expression, percentage voltage drop KLESN, and other things we can derive from the fundamental. So L4 we have computed, that is 1.38 kilometer per 1.38 kilometer, and D is 1000 kVA per kilometer square. So here I am writing all in the terms of kilo. So therefore I have not changed any expression. So if you simplify this, it will coming as 4.38%. So A is the correct answer. So now we will use this table for solving the problem. Yeah, Sangeeta, and for hexagonal service area length is multiplied by 6. Can you kindly clear the doubt? Okay, we will see that type of problem. Length is multiplied. It is not whenever we finding the total substation capacity. In that case, we multiplied with the number of feeders. If you find the one each feeder capacity, then in the question, if they are asking about the total substation capacity, then you have to multiply it with the number of feeders. So that's why in hexagon service area we multiplied with 6, not the length. I think length will not multiply with 6. One expression we will see just later. TSN is equal to 6 into SN. The TSN is equal to N into SN, and if N is equal to 6, then it will be 6 into S6. We will see. So from this table, like what are the effects of the length of feeder and K number of feeder, load density, area side of feeders, total KVA on the sorry, this length of feeder K, number of feeder, load density on the area served by one feeder, total KVA and percentage voltage drop. So if the length of the feeder gets double, then the area served by one feeder gets 4 times and total KVA gets 4 times and percentage voltage drop will get 8 times. And for the load growth, if load density gets double, then total kVA gets double and the percentage voltage drop also gets doubled. And for the when we are adding new feeders, in that case number of feeders if gets double, then area served by one feeder will gets uh, reduced to half and percentage voltage drop will gets reduced to half. And for feeder rerouting condition, k value gets half, then this percentage voltage drop get also reduced to half. So let us see the problems based on this uh, Eugen interpretation of voltage drop formula. So the first problem is that if the load density of each feeder for the problem given in question 6 is double, keeping all the parameters same, determine the percentage voltage drop. So we have seen for a square. If you don't remember, if you go by fundamental, like for a square shift distribution substation service area. So we know that percentage voltage drop is K into 2y third of L4 into D. And now the load density for each feeder is you are getting you are making it double. So it gets double. So we can see from the expression is percentage voltage drop is directly proportional to D. So percentage voltage drop will be doubled if D becomes double. So we have computed percentage voltage drop in question 6. What we got the value in question 7. We got 4.38%. So in question 7 we got 4.38%. So percentage voltage drop will be 2 into 4.38%, that is 8.76%. From the table you can also see that if you are getting if you are making the load density double, then percentage voltage drop also gets double. Either way you can solve. So A is the correct answer. Now let us see the next problem. In this problem, if the length of each feeder for the problem given in question 6 is double, keeping all other parameters except thermal capacity of line same, determine the percentage voltage drop. So we know that percentage voltage drop is K into 2 by third of L4 Q into D. So we can say that percentage voltage drop is directly proportional to L4Q. So percentage voltage drop in second case and percentage voltage drop in first case, we can compare 2L4Q divided by L4Q. So this will be percentage voltage drop 2 equal to 8 into percentage voltage drop 1, and we got percentage voltage drop for the previous problem as 4.38%. So this will give you 35.04%. So D is the correct answer. And from the table you can see that if the length of feeder gets double, then percentage voltage drop gets 8 time. So this is the case. So in either way you can solve. Yes, Rahul Patil D 80. Very good. Now let us see the next problem. Determine each feeder capacity for the problem given in question 6. So we have to find the sorry, we have to find the each feeder capacity that is represented by S4. Each feeder capacity. So we have seen that Sn is equal to Dan. So here it will be represented as S4 is equal to DF A4. Chunki since Sn is equal to Dan, and again we bifurcate S4 is equal to D into L4 square, because tan 45 is 1. We know all the values. D is given as 1000 kVA per kilometer square, and L is given as 1.38 kilometer square. So this will give you each feeder capacity, that is coming as 1904.4 kVA. So option D is correct. And in other way you can also find since the current value is also given, so in another way you can also find S4 equal to rated voltage of feeder and the rated current value, that is thermally limited value. So it is coming as root 3 times of VLL is given as 11 kV. So 11 into 1000. So it is just write in kV form only. 11 kV, and thermally limited current is 100 ampere. So from here you get S4 as 1905.2 kVA. So approximately it is coming as 1905 kVA. Yeah, D is the correct answer. Very good. Rahul Pati, he is he is solving every problem correctly. So now let us come to the next problem. I think Sangeeta, you have. I think this is in this case it gets multiplied with number of feeders if you are finding the substation size. So see this problem carefully. So determine the substation size for the problem given in question number 6. So it is question 6, not 3. So substation capacity represented by TS and 4 is representing the number of feeders. So TS4 is the total kVA supplied from a substation. From a substation. From a square substation you can write. From a square shaped distribution substation. So so this is the substation size only. So TS4 is substation size or substation capacity, anything you can say. So I want to write one thing here, since there are 4 feeders, so the substation, therefore TS4 equal to 4 into S4. 4 into S4, S4 is given as 1905 kVA. So this will be give you 7621 kVA is the answer. So D is the correct answer for this problem. So important point for this is that TSN is equal to N into SN. Sangeeta, are you talking about this point or some other point? If this is hexagonal shaped distribution substation, then here TS6 will be 6 into S6. Yeah, Rahul Patil, you are correct. Since S4 is 1905, therefore 4 feet, so total SN will be this. Very good. Okay. Now let us move to the next problem. This is the last means this question 12 to question 16 are related problems, and this is the last numerical type problems. So in this problem we have solved for a square shaped distribution substation. Now in this problem we are going to solve hexagonal shaped distribution substation. I am putting figure all here, but this figure may not be in your exam. So I am just putting so that the things will be clear to you. So in this problem, a distribution substation consists of 6 identical primary feeders with hexagonal service area. The substation is located at the center of the service area. The service area of each feeder is of triangular shape with uniform load density of 1000 kVA per kilometer square. Sorry, here a little bit mistake. The voltage of each feeder is 11 kV 3 phase. Each feeder is of thermally limited to 250 ampere. The percentage voltage drop of the feeder is given as 0.005 per kVA kilometer. Determine the substation size. So first we will find the load served by each feeder, the kVA capacity of each feeder. How we can find? We are given with the rated voltage of feeder 11 kV, and we are also given with the thermally limited capacity 250 ampere. So from there we can find the maximum load per feeder. So since this is thermally limited feeder, thermally limited, and those who are getting answer can put your answer in the chat box. Thermally limited feeder, so we can write maximum load per feeder is, maximum capacity of each feeder is S6, so it will be root 3 VLL I6. So S6 will be root 3 VLL is given as 11 kV line to line voltage, and thermally loaded capacity is 250 ampere. So it will give you 4763.14 kVA. So is the loaded capacity of each feeder. Now since there are 6 feeders, the substation size will be 6 times of this. Since there are 6 feeders, the substation size is TS6 into 6 times of S6, 6 into 4763.4 kVA. So it will give you 28,578.84 kVA. So correct answer we are getting is A, 28,578.83 kVA. Yes, Sangeeta, very good. Rahul Party, Sangeeta, both are responding. A is the correct answer. Now let us see the next problem. In this problem, determine the length of each feeder. So again we will use the rated capacity of each feeder. From there we can find the length of each feeder. There are many ways you can find the length of each feeder from the thermally loaded capacity
Sir,
of,
once uh, repeat the 12, question number 12 problems solution.
yes. So it is very simple. You have to find the substation size. So it is given that each feeder is thermally limited to 250 ampere. So that current value we got, and it is also given that the rated voltage of feeder is 11 kV. So voltage value you got. So you know the current, you know the voltage, you know the, then you can find the capacity of each feeder. So capacity of each feeder is root 3 times of line voltage into current. So root 3 times of voltage into current. So you will get, this is the rated capacity of each feeder, 4763.14 kVA. And since there are 6 feeders in the substation in the hexagonal type substation service area, then the substation size will be 6 multiplied with the each feeder capacity. So we will get this value as the answer. So don't get confused with the notations I am using. This is the uh, notation used by Sanjeev Ganguly sir and the Turan Gun in a book. So that's why we are making this notation. If the things are clear in your mind, then you can just write S is equal to root 3 V into I, and total capacity will be 6 into S. I am writing 6 independent number of feeders, and if in this problem If the problem is same for the a square shaped substation service area, then we are representing by 4, S4 and I4 and TS4. So that's why we are using S6, I6, TS6.
Sir, I have doubt here.
Yes.
In one of the slide, the TS6 was represented as 6 by root 3 DL square by 6. And here you are using, you are multiplying directly by 6, not by root 3. What's the difference?
Which slide?
Uh, in Ganguly sir, slide number 45. Let me see if I can put it on the chat.
No, I am sharing this one.
Yes, sir. This one, yes, this one is correct, sir. You see, TS6.
Yeah. So this is simple. You got this value. Like here I have see. So this is the value by solving. If you do it further, then it will get TS6 is equal to 6 into S6, and S6 you can write 6 into D times A6, that you got, and 6 times D A6. How we can write A6?
Yes.
Ln square. So it is L6 square and tan theta. And we know that if there are 6 feeders, tan theta is coming at tan 30. So 6 into dl L6 square and tan 30 is 1 by root 3. Now match with this expression with this expression. You will get same
Oh,
value. 6 divided by root
okay.
3 dl6 square. Right?
Okay. Right, sir.
Yeah. So depending upon the problem what they are asking, we have to use that. And more the problem you solve, more you will get the uh, confidence, and will be more comfortable in solving the problem. And basically in NPTEL exam, one thing I want to tell you that if you solve the assignment, if you solve the assignment just in a honest way, you will get a grade. Definitely you will get a gold certificate in elite plus gold certificate. Means if you understand the assignment and you understand this all the problems we are solving, you will definitely get elite plus gold certificate. Then no, nothing more you have to go in depth. But if you have interest, then go more in depth and learn many things. You can just elaborate and explore what you want. But if you solve assignment very in honest way, then you definitely get good percentage of marks in exam. That is sure. And basically they will ask this type of problem only. They will just play with the data. So let us solve the next problem. So in this problem we have to find the length of each feeder. So how we can find the length of each feeder? There are many ways you can apply any of the ways, any of the things you want. We know that S6 is equal to DA6, and as we have discussed, we can write A6 as first D is equal to 1000 kVA per kilometer square, and A6 is L6 square divided by root 3, because tan 30 value is 1 divided by root 3. And we know that S6 X6 is given as 4763.14 kVA So 1000 kVA per kilometer square into L6 square divided by root 3. So L6 is length of each feeder in hexagonal substation service area. So we will get 4763.14 into root 3 divided by 1000. This will become as under root 8250 divided by 1000. So we will get 8.25. So it is coming as 2.87 kilometer. So B is the correct answer. Now let us see the next problem. So next problem is that we have to find the total percentage voltage drop from the feed point to the in point of the main. So B will use the fundamental expression. Percentage voltage drop is K into effective length into Sn. That is capacity of each feeder. Sn is capacity of each feeder. So LE will be for triangular service area, because each feeder has a triangular service area. So effective length for each feeder will be 2 by third of length of feeder. So Ln. So 2 by third of L6. And Sn be also known. Sn is S6. S6 we have computed 4763.14 kVA. Capacity of each feeder. Therefore, percentage voltage drop 6 equal to K times K is given as 0.00 percentage voltage drop per kVA kilometer, and LE 2 by 3 of L6. L6 is we have computed. L6 is coming as 2.87 kilometer, and Sn we have computed 4763.14 kVA. Therefore, you will get percentage voltage drop as 4.5567%. It is approximately coming as 4.56%. A is the correct answer. Now let us see the next problem. So in this problem, if the number of feeders for the problem given above is doubled, keeping all other parameters constant, length of feeder, load density, total service area, and base voltage, determine the percentage voltage drop. So number of feeders get doubled. Number of feeders double. So if number of feeders get doubled, then what will percentage voltage drop? If number of feeders get double, it creates load under a feeder to be reduced by half. So load density reduced by half. So which results in voltage drop to be reduced by half. Therefore new, so it will be new percentage voltage drop will be also reduced by half. Percentage voltage drop, previous voltage drop is 4.56% divided by 2. So it is coming as 2.278%. It is approximately equal to 2.28%. So C is the correct answer. Because if you double the number of feeders, then load under a feeder will get reduced by half. So therefore, percentage voltage drop will also reduce by half. Now moving to the next problem. Did you get this problem? Any doubt in this problem?
No, sir. We are clear.
Yeah, so we know that percentage volt of K LESN. So if you yeah, if you are increasing number of feeders and keeping other parameters same, then you are reducing this. If you are reducing the load under a feeder, that is SN, that means percentage voltage drop also get reduced by half. So that comes to 2.28%. Now come to the last numerical type problem. So in this problem, if the load density for each feeder of the problem is doubled, keeping all other parameters constant, such as length of feeder, number of feeders, K base voltage, determine the percentage voltage drop. So here load density gets doubled. So what do you think? What should be the correct answer? Load density gets doubled. So percentage voltage drop will be what? Percentage voltage drop is directly proportional to load density. So it also gets doubled as we have seen. So new percentage voltage drop will be 2 into 4.56%. So it is 9.12%. So D is the correct answer. Yeah, Rahul Patil, Sangeeta, all of you are correct. Just one thing. So now we have four theoretical problems. Uh, just we will see this type of problems. So the distribution system is usually of isolation transformer, a step up transformer, step down transformer, D none of the above. What is the correct answer? Just tell fastly.
C, step down.
Yeah. So distribution transformer is of a step down transformer. So, so distribution transformer ratings from 10 to 50, 500 kVA are usually connected to its primary feeders, sub feeders and laterals, and this reduce distribution voltage to the utilization voltage. Utilization voltage at will the consumers consume power. So basically in India we are having 400 volt line to line voltage and 230 volt 220 to 230 volt is the phase voltage. Now the next problem, the distribution transformer converts. A option is utilization voltage level to primary distribution voltage level. B is primary distribution voltage level to sub transmission voltage level. C is sub transmission voltage level to primary distribution voltage level. D is primary distribution utilization voltage level. Yes,
Option
D.
D.
yeah, D is the correct option. Now question 19. For the parallel operation of transformer, which of the following condition is not mandatory? Options are same frequency rating, same series impedance, connected in same polarities, same phase sequence. What should be the correct answer?
C. Same polarity.
No, no, it is mandatory. So same series impedance. Be the
Option B. Yeah.
yeah, be the correct answer. Now, last problem. What will happen if the transformer operated in parallel are not connected with regard to polarity? And the options are shown over here.
Option B.
No. So incorrect polarity will result in dead short circuit. So C is the correct option. See the correct answer. So that's all for today's session. If you are having doubt, any other things to ask, you can share. Any doubt? If you want to give any advice to improve the live session, any other things you can tell. If you
सर एक्चुअली एक चीज़ मैं कहना चाहता हूँ कि सेम टाइम पे कई लाइव क्लासेस चल रही हैं लाइक कंट्रोल सिस्टम के आपके तो बड़ा डिफिकल्ट हो जाता है ज्वाइन करना सेम टाइम पे सभी क्लासेस को
okay, actually that is very problematic. We cannot do anything because we have also you can see the recorded session, but if you have personally want to solve anything, then you can mail me. But everyone has a like very different tough to get time and prepare for 2 hour session. If we don't do in weekend, then how we can do in weekdays? And in weekdays we have to do the work 9 to 6 o'clock. So it's really difficult for.
नो सर इट्स वर्क इज ओके बट एट द सेम टाइम ना डिफरेंट सब्जेक्ट कोर्स वी कैन से डिफरेंट कोर्सेज आर रनिंग लाइव क्लासेस सेम टाइम
Okay, so that actually very difficult to reschedule because in the starting only we have given by NPTL that you have to just fix your schedule because means it is very difficult to reschedule the session, and that's why they are providing recorded video. Okay, Rahul Patil saying that be a real life example. Yeah, some problems I think assignment for one problem is given very like one of the nice problem one one problem is given in diagram view. So if you solve that, really give you a good feeling after solving the problem. In assignment form, last problem, I think 7 or 8 problem. Some problems we are including, we are improving the course. I will try to include some practical problems. But many things in distribution system we are discussing that moreover practical. And if we do more practical examples, then very difficult to solve the get the expression and formula because in real scenario we have also take assumption. Okay, all good. Dharmender, sorry for this thing, but we cannot reschedule the uh, like uh,
नो नो सर वी विल सी योर लेक्चर एंड वीडियो यूट्यूब
yeah. Okay, all good. Thank you for thank you for attending,
थैंक यू
and
सर
yeah, we will meet in on the next Sunday. Thank you. Good
सर
night.
एक डाउट था।
Yes,
हेलो
yes.
सर, अभी जो हमने के का वैल्यू लिया है, तो
Yeah.
उसका कोई ऐसा स्टैंडर्ड टेबल है कि कुछ स्पेसिफिक कंडक्टर होगा या फिर कुछ स्पेसिफिक कैपेसिटी ऑफ डिस्ट्रीब्यूशन लाइन होगी, मान लो 11 kV या फिर 33 kV, कोई पैंथर या फिर ACSR कंडक्टर एक कंडक्टर यूज करते हुए, तो उसका कोई टेबल है क्या जिससे हम के का कांस्टेंट वैल्यू हमें मिल सके?
Yeah, some tables are there in Turan Guran book. I will share to you. I will share in the next
ओके सर।
next presentation.
ओके।
Okay.
सर योर ईमेल आईडी प्लीज सर
Yes. And you can contact me on WhatsApp also. I am giving my personal mobile number. I may not reply instantly, but I will reply some later time also. Okay. Thank you. Good night.